So imagine you have a system. Imagine we have a pure state, and you divide the system into two parts, A versus B, and you want to trace over the part B, and you get a reduced density matrix. So this is the wave function for the AB system. You write it as a density matrix, and you trace over the B part. And the entanglement entropy is defined just the entropy of this subsystem. And it turns out for pure state, it doesn't matter whether you trace out A or trace out B. They have the same, the so-called entanglement spectrum, and therefore they have the same entanglement, or in terms of entropy. Okay. So for example, if you have the so-called Bell state, which is a 2-qubit entangled state, 0, 0 in superposition with 1, 1. If you trace over B, the reduced density matrix for A is essentially random, has no information, so it's an identity up to a proportional constant. And you just calculate this entropy, you see that this is 1. I'm using base 2 here for the log. So it turns out that for torical, people have shown that if you divide the system into two parts, the entropy for the ground state would actually scale with the boundary, the length of the system, and with some additive constant. And this additive constant for the torical turned out to be 1. And this is the so-called topological entanglement entropy. So I would give you some flavor of the derivation used here. And for more general stringnet, I have to refer you to Xiaogan's paper. And more general quantum field theory argument, you can read Kitab and Praskill's paper. So the next entanglement measure that I want to introduce is the so-called geometric entanglement. This is very simple idea. Suppose you have a wave function. Here, imagine I have a chain of spin. And how do I define entanglement? I can define the entanglement in terms of how close to the ground, to the product state. Or if you're a condensed matter person, you would imagine that what is the mean field approximation to the wave function. So we're going to focus on the wave function, not the energy. So in some sense, the relevant quantity is the overlap of your ground state and the product state, and you want to see how good I can approximate my ground state with just product state. And this maximal overlap, I just define taking the log and take a minus sign to be my entanglement measure. So you can see that if this state is a product state itself, the overlap will be 1, and therefore the log will give you 0. But if the overlap is very small, this means that I cannot use the product state to approximate my ground state. Therefore, my ground state would have a large entanglement, meaning that the overlap would be small, and then if you take log for the minus sign, this number will be large. So this is one way to characterize the entanglement.
Will it be 0 ever?
If it's product state, it will be 0.
I mean, is there any case that you have 0 overlap with the product state? Because
no,
when you define log, you have a divergent quantity.
No, you can show that it's never going to be 0. So imagine that you write your wave function in terms of some computational basis. You can always take one of the component and then just inner product to the wave function. You always get non-zero because you try to maximize, right? If you minimize, of course, you might get 0, but you are trying to maximize. So in fact, you can show this. There's always a lower bound. So here I define the entanglement with a product state. My product state is a product of individual spin, but I could also consider my product is a block of spin. So I have many blocks. Each block has L spin here. So for this, we call it, this is a geometric entanglement of blocks. This, in some sense, is an idea of doing RG. You cross grain. Here you are asking the entanglement among all these individual spins, but here you are asking the entanglement among these blocks. Therefore, you don't care about entanglement inside. In some sense, you are trying to reduce the short range entanglement. Okay, so this entanglement can actually be measured. Okay, yes, if you know the closest product state, because then you know what is the basis that you want to measure. So the product state tell the experimentalist the basis that for you to do the, for example, the Stern-Galak measurement. Okay. Well, you say, okay, that's pretty bad. I have to know the closest product state if I don't know. But you could actually find the product state or find the best Stern-Galak setting by actually using iteration. So I just give you some intuition. So first, this is actually numerically could be implemented. This is actually very similar to DMRG doing the sweeping. So what you do is you fix, let's imagine we're doing it experimentally. We fix all the measurement bases except one. And then we just continuously rotate the measurement setting such that the outcome of that particular outcome it actually achieve a highest probability. So then you fix this, you move to the next side, you fix all the other setting, and then you rotate this setting until you get the maximal signal, and you keep doing this so on and so forth, and back and forth like DMRG sweeping. And until you converge, then the maximum, the probability that give you the maximum weight is actually giving you the entanglement. And this actually can be implemented. Numerically, you have the wave function, for example, you can write in terms of matrix product states, and you just do iteration. So for people doing tensor product state, this is, the overlap is actually a single layer contraction. So it's in some sense easy to do than computing, for example, the reduced density metric, which require a two-layer contraction. And in fact, actually, this was implemented experimentally only for 4 qubits. Okay, so I'd like to comment why we think this geometric entanglement is useful. We have, in the past, we have used this to detect the quantum phase transition, just looking at the entanglement and its singular behavior across the phase diagram. And from there, you can actually determine the quantum critical point. And this is one example. We did it for the bilinear biquadratic model. You see that these singular behaviors seem to match the transition point. And actually, I mentioned this is experimental data measuring the ground state entanglement for the XXZ model only for force spin. And you see that there's a singularity here. This actually occurred at the phase transition, even though the system is only 4Q. Okay, it could also be used to give the bounds on quantum computational resource, but I won't dwell on that.
Sorry,
Yep.
what do the axis mean in the last part?
This
Horizontal axis and the vertical.
so this gamma is the anisotropy in the system.
And the vertical.
The vertical is the entanglement, the total entanglement. I use E log 2 because it's a log and with basis 2. It's the entanglement, basically entanglement for this quantity.
So how do you measure entanglement experimentally?
So just as I described, it's the maximal signal. You find which basis give you the maximal signal, and that probability, you take a log, that's the entanglement. In experiment, we didn't do this iteratively. We know what the basis, we know the closest product state, therefore we know the basis. And then we verify it's the local maximum by varying the axis and see that entanglement, the overlap actually decreases. Okay, so maybe I will, in the following, I will just repeat what people have done to calculate the entanglement entropy for the toric code. So in order to calculate entanglement entropy, you need to get the reduced state. So this is the this is the wave function that I have. The omega here is actually 0, 0, and this G is product of these star operators that I described earlier. So all the ground state can be described in these. I mean, all the 4 basis states can be written in this form. But for the entanglement entropy, we need to partition into 2 parts. Suppose, let's do that. So I would have some partition in mind. So I'll also write these vacuum state as a 2 product of vacuum in each subsystem A and B. And the G is product of poly X operator. So I can also write those products and separate them into the product of sigma X in the A part of the spin and also the B part of the spin. Okay. Then I just take then I take the density matrix for this total wave function, and rewriting, you can just rewrite this in terms rewrite G prime in terms of G and G tilde, and tracing over the B part simply means that you same with this with the number which is becoming a number. So from this, the non-zero contribution, because this is G tilde, B is a product of sigma X operator, it will flip from 0 to 1. So therefore, these this would have non-zero contribution only if G tilde B is 1, is identity, and G tilde has to be in the group. So therefore, it makes sense to define 2 subgroups of G. So first, maybe I define, according to this condition, I like to define a subgroup where G is from the, small g is from product of sparse operator. And I want to write it in terms of A tensor product B, where I restrict the B part to be identity. So this I call subgroup A, meaning that this subgroup acts trivially on the B part, but act non-trivially on the A part. I could also define the complement one, the subgroup GB, which acts trivially on the A part. Okay. So when I write this G equal to GA tensor product GB, GA and GB need not be group element of the capital G. Only the product need to be. So this is from what I have. I assure you that if I give you the slide, you can actually follow step by step. So if you can see here that I can actually do a manipulation, because the GA, if I divide it by the GB, then this just pull out a factor of GB number here by the definition of GB. And then by direct calculation, you just square this density matrix. You find that this density matrix square is proportional to itself and with this proportional constant. So the absolute value of G indicating the number of group elements in the G. And from this actually indicates that the wave function of such bipartition actually is already in a Schmidt decomposed form, where the Schmidt coefficients are all the same. This actually indicates that the entanglement entropy actually is the same as the geometric entanglement, and in terms of this quantity. So it boils down to calculate the order of the group, subgroup GA and GB. So let me just give you an example of this. So imagine this is the lattice that we have, and the spins are on the edges. So I want to partition the purple line, the purple edges are my A, so this is my A region, and the rest is B. So we know the G, the group element is 2 to the total number of star operator minus 1. And then we have to calculate what GA is. So GA is a subgroup that acts trivially on B. So if you take the star operator here, it would act non-trivially on these B edges. If you take 1 here, it would act only on the B edges. So essentially, the number of group element is choosing any particular combination from these strings. So therefore, the GA, the group order is 2 to the NA. NA is number of star operator inside this region A. And you could also do the similar things. You find that the GB is a subgroup which the group element only act non-trivially inside B. So this would be a possible choice. And here would not be a possible choice. So these are the boundary of A. So therefore, the group element, the number of group element actually is the number of star operator inside B minus the boundary. And from the expression that I have here, this gives me the entanglement entropy. And so therefore, you get the entanglement entropy is proportional to the boundary, denoted by partial A minus 1. This one is from the constraint. Okay? Any questions so far?
Excuse me.
Yeah.
In your experiment, you said you use 4 spins.
Yeah.
And is it something, the coupling is like a square coupling?
It's on.
NMR.
It's NMR. Yeah.
And you use a molecule with the square coupling or star shape?
So they were able to do these decoupling so that it can simulate these ZZ coupling, XX, YY, and ZZ coupling. Yeah. For the detail of experimental, I have to refer you to the paper. Yeah. Yeah. I only know the theoretical part.
And so the part A contains 2 spins and part B contains 2 spins.
For the geometric entanglement, we don't need to. For that, we treat the individual spin as a product state. Yeah. We did not do the blocking yet. Yeah. Are you asking the partition?
Yes.
Yeah. So each spin is a. So the product state is product of four spin individually. Okay, but here from you can see that the entropy scale proportionally to the perimeter of the region up to this additive constant, and this is the this is actually the topological entanglement entropy. So using this as the starting point, you could actually construct various ways of extracting these topological entanglement entropy. This was in Kitab Praskel's paper, and this is in Xiaogan's paper. So the idea, you want to actually get rid of the boundary effect, and you only want to extract the constant term. So you can verify because you have 1, 2, 3, 4 that contain the minus gamma, and you have 3 terms that contain plus gamma, so therefore you get a topological contribution. But I want to comment that this scheme is valid only if the region that you have is larger than correlation length. So in reality, it's very difficult to scale your system for computational purpose so that actually your system is bigger than correlation length, except in these fixed point wave functions. How much time do I have?
40 minutes.
40 minutes. Okay, out of time. So any question? So I will have the slide available. You can just read the slide later if you have any other question. You don't need to write down anything. Okay, so what about the geometric entanglement? So these are the foreground states. So, and to compute the geometric entanglement, we need to find the maximal overlap in general, analytically, it's not always possible. So therefore, what we can hope is to find a lower bound and upper bound. And if the lower bound and upper bound actually match, then we get the exact value. Okay, so that's the strategy. And this is probably related to your question. One upper bound of the geometric entanglement is coming from the lower bound on the overlap. So because 0, 0 is one of the components, so I can just take the overlap of the ground state with a 0, 0. It's just this coefficient. So this means my maximal overlap is lower bounded by this. And this means that my entanglement is upper bounded by this quantity. This log 2G. G is the order group. Okay. But the non-trivial part is to append the lower bound on the entanglement, namely the upper bound on the overlap. But as I showed you earlier, in the derivation of the entanglement entropy, actually, we also derive the geometric entanglement for bipartition. So we like to use the bipartition to lower bound the entanglement. So how can we do that? Well, because my entanglement is defined as product state, the product for all spins, individual spin, is contained in this bipartition, right? This bipartition A and B, A could be entangled, but it certainly contains this as a subset. So if I maximize the overlap with the bipartition, this certainly would be at least as good as maximal overlap with respect to this partition. And therefore, this gives me a lower bound on the entanglement. And I just show you that we can compute the lower bound, we can compute the bipartition geometric entanglement. But the key point is you want to make the lower bound as large as possible in order to saturate the upper bound. So it turns out that the bipartition you have to choose is very strange. Initially, we think we thought we have to choose maybe A is the parallel edges and B are vertical edges. It turns out this is not the optimal. So for the optimal bipartition that we choose is such partition. So you choose this edge as in A, and somehow you loop around. You go to this A, and then this would actually go to here, and then loop around. So the point is that if you follow these edges, it will wind around just once, and then will actually touch all the vertices. So that's the key point. So why do we want to do that? Because remember, we want to maximize the end. We want to maximize the bipartition entanglement. This means that we want to minimize the order of the subgroup. We want to, so the smallest is 1. So if we could achieve that, then we get really good lower bound. And it turns out that this subgroup, with respect to this bipartition, they are trivial subgroup. So how do you see that? So if I take a star operator here, and I want to make the action on B to be trivial, in order to cancel this action, I have to apply another star operator to cancel the action on this edge, and also have to cancel this, and so on and so forth. If you follow, it would touch all the star operator. In the end, you have to apply all the star operator. That means it's identity. Okay. So the upshot is that it's quite strange that for the torical, the bipartite partition can be maximized so that actually is equal to the multipartite geometric entanglement. Okay, so the conclusion for that calculation is that the geometric entanglement with respect to all the individual spins is equal to the number of star operator -1. So the 2 to this number is the order of group element. And recall that this -1 is actually the same as that in the toric code for using the entanglement entropy. So you may think that this is just a coincidence. And we also check for the quantum double model with gauge group G. You could define that quantum double model using a similar way. So the A is very much like our star operator, which actually is a product of sigma x. But in general, you can lift it into an arbitrary group G. The quantum state is labeled by a group element. So these are the action of the A or star operator. It's simply apply all the group to these 4 edges, and then for all possible combination. And the Poincare operator is very similar to the product of sigma z, except it's becoming a group. We require that the product of each group has no flux, meaning that it multiplies to identity E. Okay. So we just define the product state with respect to the individual spin, but we could also consider some sort of coarse-graining process. We can consider flux. So for example, you can consider block of this form. So we have 4 spin here, etc. So each block has an area like square root times square root 2. You could also consider larger blocks. The question is, what is the geometric entanglement? So and then maybe just show you the result first, and then give you the detailed derivation. So the result is that the geometric entanglement is a bulk quantity, so therefore it would be proportional to the number of MB is the number of blocks, and L is the boundary size, and alpha is just some number, -1 for the toric code. In general, it will be some non-trivial topological contribution. So that's the upshot. So in some sense, this may be useful because if we could compute the geometric entanglement with different way of blocking, by increasing the block size, you have L that you could fit numerically, and then you could just get the constant. So here is the derivation. So in order to compute the geometric entanglement for the block, as I said, we don't care about the entanglement inside each block, so we're coarse-graining such that the short-range entanglement is removed. And it turns out this can be done by local unitary. So maybe let me pause for the moment. This part is somewhat technical, but it's quite interesting. Any question? So the point is that you can actually attach, for example, if you define some torical on some arbitrary lattice, you could actually attach a spin with 0 state, which is product state, and then you apply the so-called control NOT gate from this spin to that spin, and also from this spin to that spin. It would generate a different torical Hamiltonian. And the ground state is mapped to this torical Hamiltonian by the control NOT gate. And if you, for example, attach a plus spin, and then you start from this spin and perform the control NOT gate, you will actually generate a different torical Hamiltonian. So you could do the reverse. If you start with this lattice, you could actually perform the control NOT gate, and then you coarse-grain, and this additional degree of freedom can be removed. And gradually your lattice will become smaller and smaller. This is what we're going to do. This is just a pictorial way of showing the proof. We're going to remove the short-range entanglement inside the block. So what we did is use these graphical rule to gradually remove spin inside and also the star operator inside.